There is a specific temperature at which the universe prefers to exist, not the temperature of a star's surface, not the temperature of a volcanic vent on the ocean floor, not the temperature of a summer afternoon in any city, on any continent of this world. The universe's preferred temperature is 2.725 Kelvin. That is negative 270.4 degrees Celsius. That is negative 454.7 degrees Fahrenheit. That is a number so close to the absolute coldest condition that physics permits that the difference between them when plotted on any scale meaningful to human experience disappears entirely. Right now, as you sit wherever you are sitting, your body is radiating heat. Your skin surface hovers at approximately 33 degrees Celsius. The air touching your arms is somewhere between 18 and 24 degrees, depending on the room. The chair beneath you has warmed slightly from contact with your body. The floor, the walls, the ceiling, all of them sit within a narrow band of temperature that your biology accepts as normal. You are surrounded by warmth. You are made of warmth. You generate warmth with every breath, every heartbeat, every thought passing through the electrochemical machinery of your brain. You feel without thinking about it that warmth is the natural condition of things. It is not. The natural condition of the universe is 2.725 Kelvin. The natural condition of the cosmos is a cold so extreme that no winter on Earth, no polar night, no frozen ocean floor comes within a factor of 60 of approximating it. The warmth you feel right now, the warmth of your body, your room, your world, is an anomaly so statistically improbable against the backdrop of cosmic reality that the word anomaly barely begins to carry the weight of what it means. This is not a story about how cold space is. That question has a simple answer. You could look it up in 30 seconds and move on with your day. This is a story about something far more unsettling. This is a story about why the universe chose cold. Why a cosmos that began in temperatures exceeding 1 trillion degrees has spent the overwhelming majority of its existence approaching the absolute floor of thermal possibility. Why warmth, the condition you have never once in your life gone without, is among the rarest things in all of existence, and what it means that you happen to be here during the narrow window when warmth still exists at all. If these are the kinds of journeys that change how you see the world when you step outside and look up, do something small for me. Hit that like button and subscribe to this channel. It costs you nothing, and it allows me to keep making these deep dives for you. I am genuinely grateful every time someone chooses to take one of these journeys. Get comfortable. Settle in. We are going a long way from home tonight. Let's begin. Before we can talk about why the universe is cold, we need to dismantle something. There is an assumption so deeply embedded in how humans think about temperature that most people carry it their entire lives without ever examining it. The assumption is this, that cold is a thing, that it exists the way heat exists, that somewhere out beyond the atmosphere the cold of space presses against the hull of a spacecraft, the way winter presses against a window, that if you stepped outside without a suit the cold would rush in and claim you. None of that is true, and understanding why it is not true is the first step toward understanding what is actually happening in the thermal universe. Cold is not a substance. Cold is not a force. Cold is not something the universe produces or stores or directs. Cold is an absence. It is what remains when energy has left. When you say a room is cold, you are not describing something the room contains. You are describing something the room lacks. You are reporting the absence of thermal energy, the deficit of molecular motion, the gap where heat used to be or never was. This distinction sounds philosophical. It is entirely physical, and it changes everything about how we must think about temperature in space. On Earth, when you step outside on a January night in a northern city, the air attacks you. That is not metaphor. It is mechanism. Molecules of nitrogen and oxygen moving at speeds averaging several hundred meters per second collide with your exposed skin at a rate of billions of impacts per square centimeter per second. Each collision transfers a tiny quantum of energy away from your body and into the surrounding air. Your nerve endings detect this energy loss. Your brain interprets it as cold. The sensation of cold is at its most fundamental level, the sensation of your thermal energy being taken from you faster than your metabolism can replace it. The air is not cold, the air is taking. Cold is what you feel while it takes. Now, remove the air. Remove every molecule of gas, every atom of matter, every particle of dust from the space surrounding you. You are floating in the vacuum between stars hundreds of billions of miles from the nearest sun. Nothing touches you. No molecule collides with your skin. No medium surrounds your body. The mechanism through which cold announces itself on Earth, contact collision conduction, does not exist here. So what temperature is it? The question asked that way nearly stops making sense. Temperature, in the classical physical sense, is a measurement of the average kinetic energy of particles in a substance. Fast-moving particles mean high temperature. Slow-moving particles mean low temperature. In a gas, temperature tells you how vigorously the molecules are bouncing around. In a solid, it tells you how intensely the atoms are vibrating in their lattice positions. Temperature is always at its core a statement about matter in motion. Where there is no matter, or almost none, the concept of temperature begins to dissolve at its edges. A cubic centimeter of air at sea level on Earth contains approximately 27 billion molecules. That is, 27 followed by 18 zeros. They move, they collide, they exchange energy, and from that constant violent exchange emerges what we measure as temperature. A cubic centimeter of interstellar space, the space between stars in a galaxy like ours, contains on average perhaps one atom, sometimes fewer. The density is so extraordinarily low that the very concept of temperature, as a statistical property of many particles, becomes almost meaningless to apply. You cannot take the temperature of near-nothingness with any instrument designed for something. A thermometer placed in interstellar space would not report the temperature of space. It would report its own temperature. And its own temperature would depend entirely on two things: how much radiation it was absorbing from surrounding sources, and how much radiation it was emitting into the void from its own thermal energy. The instrument becomes the only subject of its own measurement. This is the first fracture in the common understanding. Space does not have a temperature the way a lake has a temperature, the way an oven has a temperature, the way your body has a temperature. Space is a vacuum. Vacuums do not have temperatures in the traditional sense. Only the objects within them do. And the temperature of any object in space is determined by a single mechanism. Not conduction, not convection, radiation alone. There are three ways heat moves between objects in nature. Conduction is direct transfer through physical contact. Touch a metal railing in winter, and heat flows from your hand into the metal through molecular contact. The electrons in the metal, which move far more freely than those in your skin, carry that thermal energy away with extraordinary efficiency. That efficiency is why metal feels colder than wood at the same temperature. It is not colder. It steals faster. Conduction requires contact. In space, there is nothing to touch. Convection is heat transfer through the movement of a fluid. Warm air rises, cool air sinks. The circulation redistributes thermal energy across a room, across a continent, across an ocean. Convection is the engine of weather. It drives ocean currents and atmospheric circulation and the slow churning of Earth's mantle. It requires a fluid medium through which matter can flow. In space, there is no fluid, there is no circulation. The void is absolutely still in a way that has no analog in any human environment. Radiation is the transfer of energy through electromagnetic waves. Every object above absolute zero emits radiation. Your body emits infrared light continuously, a constant, invisible stream of photons, carrying energy away from your skin into whatever surrounds you. The walls of the room you sit in emit infrared radiation back. A campfire emits visible and infrared radiation outward in all directions. The sun emits radiation across an enormous range of wavelengths, from radio waves, through infrared, through visible light, through ultraviolet, through X-rays. Radiation, unlike conduction and convection, requires no medium. It travels through perfect vacuum at the speed of light, carrying energy across billions of miles without losing a single photon to friction or resistance. It does not need anything to travel through. It needs only to travel. In space, radiation is everything. It is the only thermal language the vacuum speaks. Consider a spacecraft traveling between Earth and Mars. No air surrounds it. No medium conducts heat from its hull. No convection circulates warmth or carries it away. The spacecraft exists in a thermal environment defined entirely by the radiation it receives and the radiation it emits. On the sunward side, solar radiation pours in at roughly 1360 watts per square meter near Earth's orbit. That energy is absorbed by the hull heating it. On the shadowed side, no solar radiation arrives. The hull radiates its own thermal energy into the void, losing heat with nothing coming in to replace it. The result is a temperature difference across the width of the spacecraft that can exceed 200 degrees Celsius. Not because space is warm on one side and cold on the other. Space has no temperature to impose. The difference exists entirely because one side faces a radiation source and the other does not. The spacecraft is not experiencing space's temperature. It is experiencing the geometry of radiation. Now imagine that spacecraft traveling not between Earth and Mars but between stars. Imagine it crossing the 4.25 light-year gulf between our Sun and Proxima Centauri, the nearest stellar neighbor. For the vast majority of that journey, it sits far enough from both stars that the radiation arriving from either source is negligible. The Sun shrinks to a point of light slightly brighter than the other stars. Proxima remains a dim red point ahead. Neither source delivers meaningful energy to the hull. The spacecraft radiates its own heat into the void. Heat leaves, almost nothing arrives to replace it. The hull cools, and it cools toward the only source of radiation that exists in that interstellar darkness, a source so faint, so ancient, and so perfectly uniform that no human eye has ever detected it without instruments. A source that fills every cubic centimeter of space in the observable universe with equal intensity arriving from every direction at once. The spacecraft cools toward 2.725 Kelvin, not because space imposes that temperature on it, but because that is the equilibrium point, the temperature at which the energy the hull radiates outward exactly matches the energy arriving from this ancient, omnipresent background glow. That glow is the oldest light in existence, and understanding what it is, where it came from, and why it defines the thermal floor of the entire universe requires traveling back to the very beginning, to a moment when the cosmos was not cold, not dark, not empty, but something so different from its current state that the same word universe barely applies to both. That journey begins in the next chapter of this story. But before we go there, hold this thought for a moment. You now understand something that most people never examine. The cold of space is not a presence, it is an absence. It is not something that reaches out and touches you. It is the removal of everything that was keeping you warm, leaving you alone with only radiation to speak to. On Earth, you are never alone with radiation. You are surrounded by matter, air, ground walls, water, all of it, exchanging heat with you through conduction and convection, all of it buffering you against extremes, all of it participating in a constant thermal conversation that keeps you within the narrow range your biology requires. In space, that conversation ends, and what remains, what defines the thermal reality of nearly all the volume in the observable universe, is a whisper, ancient, uniform, inescapable, and almost perfectly cold. The whisper has a name, and its origin is the most dramatic story in the history of the cosmos. 1112, Claude responded. To understand what heat actually is, not the sensation of it, not the common language we use to describe it, but the physical reality underneath. You need to understand what heat actually is, not the sensation of it, not the common language we use to describe it, but the physical reality underneath. You need to think about motion. Specifically, you need to think about the motion of things so small that billions of them could fit on the period at the end of this sentence, moving so fast that they cover distances equivalent to the length of a football field in the time it takes you to blink. Everything that has a temperature is moving, not in the way a car moves down a road, not in the way a river moves toward the sea, moving internally, vibrating, oscillating, translating through space in random directions at speeds that depend entirely on how much thermal energy the substance contains. The atoms in the air around you right now are not still. They are careening through the room at an average speed of roughly 500 meters per second, colliding with each other billions of times, each second bouncing off the walls of the room, off the surface of your skin, off every object they encounter. Temperature is the name we give to the statistical average of all that motion. A hot gas is a gas whose molecules are moving fast. A cold gas is a gas whose molecules are moving slow. At absolute zero, the motion would cease entirely. The atoms would arrive at their lowest possible energy state and stop. This is why temperature requires matter. Motion requires something that moves. Take the air out of a room truly, take it out, reduce the interior to a perfect vacuum, and the concept of temperature in that space becomes undefined. You can assign a temperature to the walls. You can assign a temperature to any object you place inside. But the empty space between those objects has no temperature in any meaningful sense. It has no molecules moving at any speed. It has no kinetic energy to measure. It has nothing. This is the reality that greets any object that leaves Earth's atmosphere and travels into the void. Consider a mission to Mars, not the abstract mission of press releases and mission patches, but the actual physical experience of the journey. A spacecraft departs low Earth orbit and enters a transfer trajectory, a long elliptical arc that will carry it across roughly 225 million kilometers of interplanetary space over the course of approximately 7 months. For the entirety of that journey, the crew lives and works inside a sealed metal cylinder surrounded by vacuum. No air presses against the hull from outside. No medium carries heat away from the exterior surfaces. No convection is possible. No conduction occurs between the spacecraft and its environment, because the spacecraft's environment is in the most literal physical sense nothing. The spacecraft exists in a thermal world defined entirely by two quantities: how much radiation arrives, how much radiation leaves. On the sunward side of the hull, solar radiation pours in. Near Earth's orbit, the sun delivers approximately 1360 watts of energy per square meter of surface area facing it. That number has a name, the solar constant. It represents the power of a small space heater pressed against every square meter of illuminated surface. Without active thermal management, the sunward side of the hull would heat rapidly, climbing well past the point where metals expand and electronics fail, and the structural integrity of the vehicle becomes a question requiring urgent engineering attention. On the shadowed side of the hull, the opposite crisis unfolds. No solar radiation arrives. The hull radiates its own thermal energy outward as infrared photons. Those photons carry energy away from the surface and into the void, where they will travel essentially forever, diluting across the expanding volume of space until they are too diffuse to interact with anything. The shadowed hull loses heat with almost nothing coming in to replace it. Temperatures on permanently shadowed surfaces in deep space can drop below -150 degrees Celsius. At those temperatures, certain metals become brittle, certain lubricants freeze solid, certain electronic components fail in ways that cannot be repaired from inside the cabin. The crew never feels any of this directly. They are insulated from both extremes by the engineering of the spacecraft itself: multi-layer thermal blankets, reflective coatings, electric heaters, radiator panels. But the physics does not care about the engineering. The physics operates on the hull surfaces with indifference, roasting on one side, freezing on the other. The boundary between those two conditions crossing the width of the vehicle in a gradient so sharp it occupies only a few centimeters of metal. This is the thermal reality of space. Not uniform cold, not uniform heat, but savage extremes separated by distances smaller than the length of your hand, driven entirely by the presence or absence of a radiation source. The void itself contributes nothing. It neither warms nor cools. It is thermally inert, in the most absolute sense the phrase can carry. It simply allows radiation to pass through it without interference. Now push the spacecraft further. Move it beyond Mars, beyond Jupiter, beyond the orbit of Neptune, out into the cold dark of the outer solar system where the sun has shrunk to a bright star among stars, and its radiation has thinned to a fraction of its near-Earth intensity. The inverse square law governs this thinning with mathematical precision. Double your distance from the sun and the radiation you receive drops to 1/4. Triple the distance and it drops to 1/9. At the distance of Neptune, roughly 30 times Earth's distance from the sun, solar radiation has fallen to approximately 1/900th of its value at Earth's orbit. The sun still shines. It is still the dominant radiation source in the local environment. But it no longer dominates the way it does in the inner solar system. It has become one voice among many, rather than the only voice speaking. Continue outward. Cross the heliopause, the boundary where the sun's solar wind is no longer strong enough to push back against the interstellar medium. You are now in interstellar space. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter the space between stars. At the time of its crossing, it was traveling at roughly 17 kilometers per second and had been in flight for 5 years. It is currently the most distant object humanity has ever launched, and in the scale of the galaxy, it has gone essentially nowhere. The nearest star beyond our sun sits 4.25 light-years away. Voyager 1 at its current speed would require approximately 7,300,000 years to cover that distance if it were headed in that direction, which it is not. In interstellar space, the sun has become a very bright star. Its radiation still arrives, but thinned by distance to near irrelevance for thermal purposes. The light of all other stars in the galaxy arrives as well, but each star is so far away that its individual contribution is negligible. The combined starlight of the entire Milky Way arriving at a point in interstellar space delivers only a tiny fraction of the energy that a single candle would provide at arm's length. An object floating in interstellar space, far from any individual star, would cool. It would radiate its own thermal energy outward. The energy leaving would exceed the energy arriving from all stellar sources combined. The object would cool and cool and cool, shedding its warmth into the dark in the form of infrared photons streaming away in all directions. Its temperature would fall through the familiar benchmarks of extreme cold, past the freezing point of carbon dioxide, past the temperature at which nitrogen becomes a liquid, past the boiling point of liquid helium, and then the cooling would slow, not stop but slow. Because even in interstellar space, even in the darkest, emptiest regions between galaxies, something is arriving. Something faint, something ancient, something that exists not because any local source is producing it, but because the entire history of the universe is producing it from every direction simultaneously, at every point in space without exception. This radiation is so faint that no human sense can detect it. It carries so little energy per photon that a single visible light photon from the sun contains roughly 1 billion times more energy. It peaks not in the visible spectrum but in the microwave range at wavelengths of a few millimeters. If you could see it, and you cannot, not with eyes, not with any biological instrument, the entire sky would glow with it uniformly. Not brightly, not dramatically. A dim, perfectly even, perfectly cold light, filling every direction with equal intensity. This is the cosmic microwave background, and it sets the thermal floor of the universe. The object cooling in interstellar space would reach equilibrium when its outgoing radiation exactly balanced the incoming radiation from this background glow. At that point, it would stop cooling, its temperature would stabilize, and that temperature, the equilibrium temperature of an isolated object in deep space, with no other energy sources, is 2.725 Kelvin. To truly feel the weight of that number, you need reference points. Not abstract scientific ones, but physical ones. Things you can hold in your mind as images. Liquid nitrogen is the substance scientists use to flash freeze biological samples. A rose dunked into liquid nitrogen becomes so brittle it shatters when struck. Liquid nitrogen boils at 77 Kelvin. The cosmic background temperature is more than 28 times colder than liquid nitrogen. Liquid helium is the coldest commonly available substance on Earth. It is used to cool the superconducting magnets in MRI machines and particle accelerators. Liquid helium boils at 4.2 Kelvin. The background temperature of the universe is colder than liquid helium. To achieve temperatures below 2.725 Kelvin in a laboratory requires not just cryogenic equipment but active refrigeration systems that consume significant electrical power and require constant maintenance. The universe achieves this temperature passively, effortlessly across billions of light-years of empty space, simply by existing and expanding. The coldest natural temperature ever recorded on Earth was measured at the Soviet Vostok Station in Antarctica on July 21, 1983. The thermometer read -89.2 degrees Celsius. That translates to approximately 183.9 Kelvin. The most extreme cold our planet has ever produced in its natural environment is roughly 68 times warmer than the thermal baseline of the cosmos. Hold that for a moment. The most savage cold Earth's climate can generate the kind of cold that freezes exposed skin in seconds, that makes breathing feel like inhaling broken glass, that has killed experienced polar explorers, is 68 times warmer than what the universe considers its resting state. Our planet's most lethal cold is the universe's temperate afternoon. But why 2.725 Kelvin specifically? Why not colder? Why not warmer? The answer to that question is the answer to everything about the thermal history of the cosmos. And it requires going somewhere that no instrument has ever directly observed, and no human mind can fully picture, but that the mathematics of physics describes with extraordinary precision. It requires going back to a time when the universe was not cold at all, not slightly warm, not moderately hot, but a temperature so extreme that the number itself becomes almost meaningless as a description of physical reality. The universe was not always a cold, dark void, punctuated by scattered stellar fires. It was once, for a brief and violent instant, the hottest thing that has ever existed or ever will exist in the entire history of space and time. The transition from that primordial furnace to the 2.725 Kelvin whisper we measure today is not a story of heat being destroyed. Energy cannot be destroyed. It is a story of heat being diluted, stretched, spread across a volume so vast that the original fire has become, after 13.8 billion years, something barely distinguishable from nothing at all. Understanding that transition requires understanding what the universe was doing in the moments after its beginning. Not the beginning itself. Physics as we know it breaks down at the very first instant, and anyone who tells you with confidence what happened at time zero is telling you more than the mathematics currently supports. But the moments after, the first second, the first minutes, the first hundreds of thousands of years, that story is told not in speculation but in observations, in the precise measurements of the background radiation that surrounds us, in the ratio of hydrogen to helium in the oldest stars, in the large-scale structure of the universe itself. The universe we inhabit carries within it, if you know how to read it, a complete record of its own thermal history. And that history begins not with cold, but with a heat so absolute it erases everything you thought you knew about temperature. The next chapter of this story takes us there. 13.8 billion years ago, there was no cold, there was no dark, there was no empty space waiting to be filled, no void extending in any direction, no distance between any two points, because points themselves did not yet exist. Space was not present. Time was not present. The concepts we use to locate ourselves in reality, here, there, before, after, near, far, had no reference. Nothing existed to which they could be applied. And then something happened. Not an explosion in space, an explosion of space. The event we call the Big Bang was not a detonation occurring inside a pre-existing emptiness, the way a bomb detonates inside a room. It was the creation of the room itself, along with everything the room would ever contain. Space came into existence and immediately began expanding, carrying with it energy densities and temperatures so extreme that no analogy drawn from human experience can do them justice. The closest physics can get to describing the first measurable instant, roughly 10 to the power of -43 seconds after the beginning. A duration called the Planck time involves temperatures exceeding 10 to the power of 32 degrees Kelvin. That is a 1 followed by 32 zeros. The surface of the Sun at approximately 5500 degrees Kelvin is cooler than that primordial temperature by a factor so large that writing it in standard notation would fill this page and several more. Every particle of matter and energy that would eventually become galaxies, stars, planets, oceans, living cells, and the neurons firing in your brain as you process these words existed in that first instant as an undifferentiated plasma of unimaginable density and heat. There were no atoms. There were no atomic nuclei. There were no protons. There were barely even quarks in any stable configuration. The temperature was so extreme that the fundamental forces of nature behaved differently than they do today, and the particles we consider elementary dissolved into a soup of pure energy so dense that the distinction between matter and radiation was itself not yet meaningful. The universe was not hot the way a fire is hot or the way a star is hot. It was hot in a way that has no name in human language because nothing in human experience approximates it, and it began cooling immediately. The cooling happened because the universe was expanding. As space expanded, the same amount of energy spread across an ever-growing volume. Energy density dropped, temperature fell. This is the fundamental thermal mechanism of cosmic history, and it has been operating continuously for 13.8 billion years without pause. Every moment the universe grows slightly larger. Every moment the energy within it spreads slightly thinner. Every moment the temperature drops by an amount too small to measure with any current instrument, but absolutely real, absolutely relentless, and absolutely inevitable. In the first second after the Big Bang, the temperature fell from its incomprehensible initial value to roughly 10 billion degrees Kelvin. 10 billion degrees is still hotter than the core of the most massive stars. It is still a temperature at which atomic nuclei cannot hold together, at which matter and radiation exist in a state of violent thermal equilibrium, constantly converting back and forth between particles and energy and particles again. But it represents a cooling of more than 99.999999% of the original temperature in less than 1 second. The universe shed heat at a rate that makes any earthly process look glacial by comparison. During the first 3 minutes, the temperature fell below 1 billion degrees. This crossing was critical. At temperatures below roughly 10 billion degrees, protons and neutrons could begin to stick together without being immediately torn apart by the ambient thermal energy. For a brief window lasting only a few minutes, the universe operated as a nuclear fusion reactor on a cosmic scale. Protons and neutrons combined to form deuterium. Deuterium nuclei merged to form helium. Small amounts of lithium assembled from slightly more complex reactions. This process, which physicists call Big Bang nucleosynthesis, produced the primordial mixture of elements from which everything in the universe would eventually be built. The window closed when the temperature dropped too low for fusion to continue. The universe was approximately 20 minutes old. The ratio of hydrogen to helium was fixed at roughly 3:1 by mass 3/4. Hydrogen 1/4 helium, with trace amounts of lithium and essentially nothing heavier. Every element above lithium in the periodic table, every carbon atom in every living cell, every iron atom in every human blood cell, every oxygen atom in every breath ever taken by any living thing would have to wait for stars to be born and die before it could exist. The universe at 20 minutes old was a hot opaque plasma. Not opaque, the way fog is opaque, where you can see a few meters before the light scatters into nothing. Opaque in an absolute sense. A photon, a particle of light, could not travel more than a microscopic distance before colliding with a free electron and scattering in a random new direction. The universe was filled with light blazing with radiation in every cubic centimeter of space, but that light was trapped, pinballing between electrons, going nowhere. Every direction was a wall of impenetrable glowing fog. This condition persisted for a very long time. Not minutes, not years, hundreds of thousands of years. For roughly 3,800,000 years after the Big Bang, the universe remained a hot, dense, opaque plasma, slowly cooling as it expanded but still too hot for electrons to bind to atomic nuclei. The temperature needed to fall below approximately 3000 Kelvin before that binding could occur. And 3000 Kelvin, while cool compared to the first seconds, is still the temperature of a red-hot heating element, the temperature of the surface of the coolest stars. The universe needed to cool from 10 billion degrees to 3,000 degrees, and even at cosmic expansion rates that took nearly 400 millennia. Then the threshold was crossed. Physicists call the event that followed recombination, though the name is imprecise. It implies that electrons and nuclei had been combined before and were rejoining. They had not. This was the first combination. For the first time in cosmic history, electrons slowed down, lost enough thermal energy to be captured by atomic nuclei and held there. Protons grabbed electrons and became neutral hydrogen atoms. Helium nuclei captured 2 electrons each. The free electrons that had been scattering photons in every direction disappeared into atoms, and the universe became transparent, not gradually, not over millions of years. The transition was on cosmic timescales nearly instantaneous. When the free electrons were removed from the equation, the photons that had been trapped for hundreds of thousands of years were suddenly free. There was nothing left to stop them. They streamed outward in straight lines in every direction, carrying with them information about the conditions of the universe. At the precise moment of their liberation, the temperature, the density variations, the slight unevenness of the plasma that would eventually grow under gravity's patient hand into everything visible in the night sky. Those photons have been traveling ever since, 13.8 billion years, in straight lines, through the expanding universe, arriving today from every direction simultaneously. They are the oldest electromagnetic signal the cosmos will ever produce. Every other source of light, every star, every galaxy, every quasar, every explosion of any kind came after the universe became transparent. These photons were there first. They were the first light to travel freely through space. They are still traveling, but they do not arrive as the light they were. When they were released at recombination, these photons were visible light. The universe at that moment glowed like the surface of a cool star, a deep, dim reddish-orange light in every direction. If you could have been present at that moment, suspended somehow in the cooling plasma and surviving the conditions, every direction you looked would have glowed with that same red light. There would have been no darkness anywhere, no shadows, no contrast, no stars, no structure. Just a uniform glowing fog stretching to infinity in every direction, the entire sky. A single unbroken source of orange-red light. Since that moment, the universe has expanded by a factor of approximately 1100. Every distance in the cosmos is now 1100 times larger than it was at recombination. And every photon traveling through that expanding space has been stretched along with it. This stretching is called cosmological redshift. It is not the Doppler effect you might be familiar with from the shifting pitch of a passing siren. It is something more fundamental. The wavelength of the photon increases because the space it is traveling through is physically growing. The photon does not lose energy to any collision or interaction. The space itself pulls the photon longer. Longer wavelength means lower energy. Lower energy means lower temperature. The photons that left recombination as visible light with wavelengths of less than a micrometer and a characteristic temperature of 3000 Kelvin have been stretched over 13.8 billion years of cosmic expansion until their wavelengths now measure several millimeters. They have crossed the entire electromagnetic spectrum, from visible light, through infrared, through microwave, shifted so far from their origin that no biological eye in the universe could detect them. Their effective temperature has fallen from 3000 Kelvin to 2.725 Kelvin. The afterglow of creation is still here. It surrounds you right now, arriving from every direction at once, passing through the walls of your room, through your body, through the earth beneath your feet. Roughly 400 photons from the cosmic microwave background pass through every cubic centimeter of space, including the cubic centimeter your brain currently occupies every second. You have never felt them. You cannot feel them. They carry so little energy that no biological sensor could register their arrival. But they are there. They have always been there every moment of your life, every moment of human history, every moment since the universe became transparent. The discovery of this radiation is one of the most human stories in the history of science. It involves not triumph or careful planning, but frustration pigeons and a phone call between two groups of scientists who were each holding half of the most important puzzle in cosmology without knowing the other group existed. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were not cosmologists. They were engineers and physicists tasked with improving the sensitivity of a large horn-shaped radio antenna that had been built originally to communicate with early satellites. Penzias and Wilson were meticulous, careful, precise. They wanted their measurements to be as clean as possible, which meant eliminating every source of noise they could identify. They found a noise they could not eliminate. It was faint. It was constant. It arrived from every direction equally, regardless of where they pointed the antenna. It did not change with the time of day or the season of the year. It did not correspond to any known astronomical source, any human radio transmission, any identifiable interference. They checked their equipment exhaustively. They recalibrated every component. They checked again. The noise remained perfectly steady, perfectly uniform, perfectly inexplicable. At one point, they noticed that a pair of pigeons had nested inside the horn of the antenna. The birds had coated the interior with what Penzias and Wilson delicately described in their scientific paper as a white dielectric material, pigeon droppings. They caught the pigeons, relocated them, and carefully cleaned the antenna. The noise remained unchanged, indifferent to the removal of the pigeons and their deposits. The signal corresponded to a thermal source at approximately 3.5 Kelvin, just above absolute zero, coming from everywhere at once. Penzias and Wilson spent months searching for an explanation and found none. They were aware that something was in their data that they could not account for. What they did not know was that 40 miles away at Princeton University, a group of theoretical physicists led by Robert Dicke had independently predicted the existence of exactly this signal. Dicke and his colleagues Jim Peebles, Peter Roll, and David Wilkinson had worked out that if the Big Bang theory was correct, the early universe should have left behind a thermal radiation field that would today appear as microwave radiation at a temperature of just a few Kelvin. They were in the process of building their own antenna to search for it. The phone call that connected the two groups is one of those moments in scientific history that belongs more to literature than to technical journals. Dicke was meeting with his colleagues when the call from Bell Labs came through. He listened. He asked a few questions. He put the phone down and turned to the room. By most accounts, he said something to the effect that they had been scooped. What Penzias and Wilson had spent months trying to explain away was the thing Dicke's group had been racing to find. The persistent noise in a New Jersey antenna was the remnant heat of the Big Bang, the oldest light in the universe, arriving after a journey spanning 13.8 billion years. Penzias and Wilson received the Nobel Prize in Physics in 1978. Dicke, despite having provided the theoretical framework that explained their discovery, did not share in the prize, a decision that remains one of the more quietly controversial choices in the history of the Nobel Committee. The measurement that Penzias and Wilson made in 1964 was crude by the standards of what followed. Their value of 3.5 Kelvin carried significant uncertainty, but the discovery opened a door that could not be closed. In the decades following, increasingly sophisticated instruments narrowed and refined and deepened the measurement until the cosmic microwave background became not merely a confirmation of the Big Bang, but the single richest source of cosmological data available to science. NASA's Cosmic Background Explorer satellite, launched in 1989, measured the spectrum of the background radiation with a precision that astonished even the scientists who built it. The data fit the theoretical prediction for a perfect thermal radiator, what physicists call a black body, so precisely that the measured points were indistinguishable from the theoretical curve. The match was so perfect that when John Mather presented the result at a meeting of the American Astronomical Society, the audience responded with a standing ovation. Scientists rarely give standing ovations to graphs. This one deserved it. The temperature was pinned down to 2.725 Kelvin, with an uncertainty of less than 1/1000th of a degree. COBE also detected something else, something that would ultimately prove more scientifically significant than the temperature measurement itself. The radiation was not perfectly uniform. Across the sky, tiny temperature variations existed, some directions slightly warmer than the average, some slightly cooler. The differences were minuscule, roughly 1 part in 100,000. A thermometer sensitive enough to detect them would need to distinguish between 2.725 Kelvin and 2.7251 Kelvin across different regions of the sky. These fluctuations were not noise, they were signal. They were the imprint of density variations in the early universe regions that were slightly denser than average and slightly warmer at the moment of recombination, and regions that were slightly less dense and slightly cooler. The denser regions had slightly stronger gravitational pull. Over the billions of years that followed, recombination, that tiny gravitational advantage, compounded. Denser regions attracted surrounding matter. Matter fell inward. Density increased further. Eventually, after hundreds of millions of years, the first stars ignited in the densest of these regions, and the process of cosmic structure formation began. Everything you have ever seen, every star visible in the night sky, every galaxy and every photograph taken by every telescope ever built, traces its existence back to those 1 in 100,000 fluctuations in temperature of the cosmic microwave background. The seeds of all structure were planted at recombination, preserved in the radiation that was released when the universe became transparent, and carried across 13.8 billion years to be measured by instruments built by the descendants of the very structures those seeds eventually produced. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped those fluctuations with 35 times the angular resolution of COBE. The Planck satellite, launched by the European Space Agency in 2009, pushed further still, mapping the entire microwave sky at 9 different frequency bands with sensitivity and resolution that revealed structure in the fluctuation pattern down to angular scales smaller than the diameter of the full moon. The resulting maps, the most detailed images of the early universe ever produced, look like oval canvases covered in irregular patches of slightly different colors, warm spots in reds and oranges, cool spots in blues and greens. A portrait of the cosmos as it appeared at 3,800,000 years of age, a baby picture of the universe. From the pattern of those fluctuations, cosmologists extracted the composition of the cosmos with percent-level precision. Ordinary matter atoms, the substance of stars and planets and every living thing, makes up approximately 4.9% of the total energy content of the universe. Dark matter, a substance that interacts gravitationally but not electromagnetically, and therefore cannot be directly observed, accounts for roughly 26.8%. Dark energy, the mysterious quantity driving the accelerating expansion of space, constitutes the remaining 68.3%. These numbers, derived from the temperature variations in ancient microwave radiation, agree independently with measurements from gravitational lensing, galaxy clustering, and supernova brightness. The cosmic microwave background is not merely one measurement among many. It is the foundation on which the entire structure of modern cosmology rests, and all of it traces back to a temperature 2.725 Kelvin, the exhausted remnant of a fire that burned at 1 trillion degrees, stretched and cooled and diluted over 13.8 billion years of cosmic expansion until it became the faintest possible whisper of its former self, still here, still measurable, still encoding in its temperature and its fluctuation pattern the complete history of the universe from its first moments to the present day. The warmth of the beginning became the cold of the present, not because heat was lost or destroyed, because space grew, because expansion dilutes, because the universe is larger now by a factor of 1100 than it was when that light was first released, and larger still than it was when the first temperatures exceeded all comprehension, and it continues to grow with every passing second, stretching the radiation within it toward longer wavelengths and lower energies, cooling the background temperature, fraction by fraction, toward a floor it will approach but never reach. The 2.725 Kelvin we measure today is not the end of the cooling, it is a point along the way. The universe is still getting colder. 1116, Claude responded. Begin with something familiar. Begin with something familiar. Begin with the solar system, because the solar system is the only piece of the universe humans have explored directly, the only region where our instruments have traveled in person, the only corner of the cosmos whose thermal architecture we understand not from inference and observation, but from direct measurement taken by machines we built and launched and tracked across decades of interplanetary flight. The solar system is warm, not entirely, not uniformly, but compared to what surrounds it, extraordinarily so. The Sun sits at its center, a sphere of plasma, 1.4 million kilometers in diameter, fusing hydrogen at its core at temperatures of approximately 15 million degrees Kelvin. Its surface radiates at roughly 5,500 degrees Kelvin, pouring energy outward in every direction at a rate that would power human civilization for approximately 27 years with every single second of its output. This energy spreads outward through the solar system, warming everything it touches according to the inverse square law, falling in intensity with the square of the distance, reaching Mercury as a scorching flood, arriving at Earth as the precisely calibrated warmth that makes liquid water possible, thinning across the outer planets to a pale fraction of its inner system intensity. At Earth's distance, the Sun delivers that figure of approximately 1360 watts per square meter to any surface facing it directly. Enough to warm a planet, enough to drive weather systems spanning continents, enough to power photosynthesis in every leaf of every plant that has ever grown in every forest that has ever existed on this world. At Jupiter's distance, roughly 5 times farther from the Sun, solar intensity has fallen to approximately 51 watts per square meter. Still detectable, still thermally significant, still the dominant radiation source in the Jovian system, warming the cloud tops of that enormous planet and driving the dynamics of its atmosphere. At Neptune's distance, roughly 30 times Earth's distance from the Sun, the number has fallen to approximately 1.5 watts per square meter. The Sun is still visible from Neptune, it would appear, as an intensely bright star, far brighter than any other object in the sky, but recognizable as a star rather than as the overwhelming presence it is from Earth. Voyager 2, which flew past Neptune in 1989, sent back images of the planet and its moon Triton, revealing a world of pale blue methane clouds and a surface cold enough to freeze nitrogen into polar ice caps. The average temperature at Neptune's cloud tops hovers around negative 214 degrees Celsius. Triton's surface reaches negative 235 degrees Celsius, making it one of the coldest surfaces measured anywhere in the solar system. Cold, but not as cold as what lies beyond. Move outward through the Kuiper Belt, the ring of icy bodies beyond Neptune's orbit where Pluto resides. Move through the scattered disk, the region of perturbed cometary objects flung into distant orbits by gravitational interactions with the giant planets. Move into the theoretical Oort cloud, the vast spherical shell of cometary nuclei that may extend a quarter to halfway to the nearest star. A region so distant that the Sun provides almost no thermal energy and gravitational influence is barely sufficient to hold the objects in bound orbits. The temperature of objects in the Oort cloud approaches the cosmic microwave background floor. They are warmed almost exclusively by the ancient radiation that fills all of space. They sit at temperatures perhaps 3 or 4 Kelvin above the universal baseline. They are, for all practical purposes, as cold as anything in the universe can naturally be. And yet even the Oort cloud, this vast, cold, dark shell of primordial ice extending perhaps 1 to 2 light-years from the Sun, sits entirely within the Sun's gravitational domain. It is still technically part of the solar system. It is still technically under the thermal influence of a star. Beyond it begins the true interstellar medium, the space between stars, the domain where no single star's radiation dominates, where the only thermal input comes from the combined distant light of all the stars in the galaxy and from the cosmic microwave background itself. The distance to the nearest star, Proxima Centauri, is 4.25 light-years. In kilometers, that is approximately 40 trillion. In any unit that connects to human experience, it is a number that defeats comprehension. But try this. If the distance from the Earth to the Sun, 150 million kilometers a distance, light crosses in 8 minutes, were reduced to the length of a single step, roughly 1 meter, then the distance to Proxima Centauri would be approximately 270 kilometers. Not across a room, not across a city, across an entire country. You could take 1 step to reach the Sun. You would need to walk for 3 days, without stopping to reach the nearest star. And between those 2 points scaled to this model, essentially nothing exists. A near-perfect vacuum at temperatures near the cosmic floor. The solar system's warmth is real, but it is an island. A single warm room in a structure that extends for the equivalent of hundreds of kilometers in every direction and contains almost nothing else. Now zoom out further. Hold the entire solar system, all 8 planets, all the moons, all the asteroids and comets and dwarf planets, the entire region of space within a few light years of the sun in your mind as a single point, a dot. The dot is warm. The dot contains a star. Now consider how many such dots exist in the Milky Way. Estimates vary depending on the methods used and the assumptions made about the faint end of the stellar mass distribution, but the most widely accepted figures suggest the Milky Way contains somewhere between 200 billion and 400 billion stars. Each one is a dot of warmth. Each one heats a small sphere of space around itself. Each one is separated from its neighbors by distances comparable to the one between our Sun and Proxima Centauri. The average distance between stars in our galactic neighborhood is roughly 4 to 5 light-years. In the model where 1 meter represents the Earth-Sun distance, that average stellar separation is comparable to walking several days in any direction before encountering another warm dot. The Milky Way is by volume almost entirely empty space at temperatures near the cosmic background. The stars are real, their warmth is real, but they are scattered through a volume so vast that their collective thermal influence, when averaged across the entire galactic disk, is negligible. The galaxy is not a warm place. The galaxy is a cold place that contains warm things. The Milky Way's disk spans roughly 1,000,000 light-years in diameter and perhaps 1,000,000 light-years in thickness. Its total volume is on the order of several trillion cubic light-years. Divide that volume by the number of stars, and each star commands, on average, a private territory of roughly 20 to 40 cubic light-years. 20 to 40 cubic light-years of cold, dark, near-empty interstellar space surrounding each stellar furnace, isolating each point of warmth from the next by distances that take light itself years to cross. The interstellar medium that fills this space is not nothing. It contains thin gas and dust, cosmic rays, magnetic fields, the remnants of ancient stellar explosions, but its density is so low that it fails to provide meaningful thermal energy to anything passing through it. The average density of the interstellar medium in the Milky Way's disk is roughly 1 atom per cubic centimeter. A cubic centimeter of air at sea level on Earth contains approximately 27 billion atoms. The interstellar medium is 10 billion times less dense than the air you breathe. It is for thermal purposes indistinguishable from vacuum. Now, zoom out again, further, far enough that the Milky Way itself becomes a single object, a disk of stars visible as a whole. At this scale, galaxies become the fundamental units of structure, and the distribution of galaxies across the universe reveals something extraordinary, something that changes the entire picture of cosmic thermal architecture. Galaxies are not scattered randomly through space. They are not distributed evenly like raisins in a bread, spread with statistical uniformity across the available volume. They are organized, arranged into a structure of staggering complexity and scale that emerged over billions of years from the tiny density fluctuations imprinted on the universe at the moment of recombination, those 1 in 100,000 temperature variations in the cosmic microwave background that COBE and WMAP and Planck mapped with such extraordinary precision. The structure has a name, the cosmic web. Imagine, if you can, a 3-dimensional network of filaments, long thin strands of galaxies and gas stretching across hundreds of millions of light-years, curving and intersecting and forming a foam-like architecture that spans the entire observable universe. Where filaments intersect, matter accumulates into dense knots called galaxy clusters, the most massive, gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, plus enormous quantities of hot gas and dark matter, all held together by collective gravity. Along the filaments themselves, galaxies string out like beads on an irregular thread drawn by the gravitational pull of the underlying dark matter scaffolding. And between the filaments, Between the clusters, between the beads on the threads, stretch the voids. The voids are not merely empty regions between galaxies. They are the dominant structural feature of the universe. They are enormous. They are numerous. And they define the thermal character of the cosmos at its largest scales more completely than any other single feature. A typical cosmic void spans somewhere between 100 and 300 million light-years across. To cross one at the speed of light would require between 100 and 300 million years of continuous travel. Inside those boundaries, the density of matter drops to roughly 10 to 20% of the cosmic average. Galaxy formation barely occurs in voids. Stars do not ignite in meaningful numbers. Supernova explosions are rare. The radiation environment inside a cosmic void is dominated almost entirely by the cosmic microwave background, with negligible contributions from the few isolated dwarf galaxies that drift through the emptiness. The largest known voids exceed these typical dimensions by significant margins. The Boötes void, one of the first supervoids to be identified, stretches approximately 330 million light-years across and contains fewer than 60 known galaxies in its interior. Our own local group of galaxies, the collection that includes the Milky Way Andromeda and more than 50 smaller satellite galaxies, spans roughly 10 million light-years. The Boötes void is 33 times wider than our entire local group and contains roughly the same number of galaxies spread across that vastly greater volume. Inside the Boötes void, the nearest galactic neighbor might be tens of millions of light-years away in any direction. Consider what that means for a hypothetical observer at the center of such a void. On Earth, we look up and see a night sky populated with stars, thousands visible to the naked eye, billions more accessible to telescopes, organized into the faint band of the Milky Way stretching across the darkness. Beyond our own galaxy, we can detect the glow of neighboring galaxies, the smudge of Andromeda, visible to the naked eye under dark skies. The more distant members of our local group, accessible to small telescopes. We know we inhabit a galaxy because we can see structure in the distribution of stars, and because we can detect with appropriate instruments the presence of other galaxies at various distances. An observer at the center of the Boötes void would have a profoundly different experience. Their own galaxy would still be present, its stars still visible, but beyond the local stellar population, the sky would be nearly blank. No nearby galaxy clusters, no visible neighbors, no local group equivalent. The nearest external galaxies would be so distant that detecting them would require instruments far more powerful than anything humanity has yet built. An astronomer in that hypothetical civilization working with technology equivalent to ours might spend centuries studying the cosmos and conclude that their galaxy was the only one. The universe beyond might appear to any instruments at their disposal to be simply empty. They would be living inside the thermal equivalent of deep interstellar space, scaled up by a factor of millions. Their sky would be almost perfectly dark beyond their own stars. The radiation environment of their entire cosmic neighborhood would be dominated by the 2.725 Kelvin microwave background, with no galaxy clusters nearby to contribute X-ray emission, no dense filaments to scatter starlight, no gravitational lenses to magnify distant objects into. Visibility. They would be warm inside their solar system, inside their star's thermal influence, surrounded by a void so complete that the concept of cosmic neighborhood would be essentially meaningless. Scientists estimate that cosmic voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments and walls and clusters where galaxies concentrate crowd into the remaining 10 to 20%. This is the large-scale thermal architecture of the cosmos, stated as plainly as the data allows. 8 or 9 out of every 10 cubic light-years of observable universe exist inside structures where galaxy density is suppressed, star formation is negligible, radiation sources are absent, and the thermal environment is determined almost entirely by the cosmic microwave background. The Sloan Digital Sky Survey, which measured the positions and distances of hundreds of millions of galaxies over more than 2 decades of operation, produced maps of the large-scale structure that make this architecture visible in a way that no verbal description can fully convey. Looking at those maps, two-dimensional slices through the three-dimensional distribution of galaxies, you see the cosmic web as a visual fact rather than an abstract concept. Bright points and threads form an intricate network across the image, and surrounding those threads occupying the vast majority of the area of every map, stretching between every filament and around every cluster darkness. The voids, enormous irregular overlapping regions of near emptiness that define the visual character of the maps far more completely than the bright structures within them. The bright parts are the exception, the dark parts are the rule. This is not a controversial statement. It is a direct reading of the data that took decades and hundreds of millions of measurements to assemble. The universe at its largest scales is a structure of emptiness laced with thin threads of matter. The emptiness is not a background against which the structure exists. The emptiness is the structure. The voids are not gaps between things. The voids are the thing. The filaments and clusters are the minority feature, the thin scaffolding that traces out the boundaries of the dominant emptiness. Every cubic light-year of void space sits at temperatures near 2.725 Kelvin. No local source warms it. No stellar radiation penetrates it in any meaningful quantity. The ancient background radiation fills it uniformly and completely as it fills all of space, but nothing adds to that background's warmth inside the void volume. The temperature of those regions will remain near the cosmic floor for billions of years, declining slowly as the universe expands and the background radiation continues to cool, never rising, never deviating, as patient and absolute as physics itself. Even outside the voids, even within the filaments and clusters where galaxies do exist, the thermal picture remains overwhelmingly cold. Galaxy clusters contain thousands of galaxies, but galaxies are small relative to the space between them within a cluster. The intracluster medium, the hot gas that fills the space between galaxies in a cluster, is genuinely hot, reaching temperatures of tens of millions of degrees Kelvin, heated by gravitational compression as matter fell together to form the cluster over billions of years. It is one of the hottest sustained thermal environments in the modern universe. But consider the density. The intracluster medium, despite its extreme temperature, contains only a few thousandths of an atom per cubic centimeter. A gas can be arbitrarily hot in terms of particle velocity, while simultaneously containing almost no thermal energy per unit volume, because thermal energy depends not just on temperature, but on the number of particles present. The intracluster medium is hot, the way a single spark is hot. The temperature at the point of the spark is real, but the energy it contains is trivial compared to a warm room filled with air. Walk through the intracluster medium and you would feel nothing. No warmth, no heat transfer to your skin. The particles are moving at velocities corresponding to millions of degrees, but they are so sparse that the probability of any one of them colliding with your body in any given second is negligibly small. You would still radiate your own body heat into the void. You would still cool. The surrounding plasma, despite its nominal temperature in the millions of degrees, would contribute essentially nothing to warming you. You would freeze in the intracluster medium of a galaxy cluster just as surely as you would freeze in the cold dark of an intergalactic void. This distinction between temperature as a property of individual particles and thermal energy as a property of a volume of space is essential to understanding why the universe is cold even in its apparently hot regions. Temperature tells you about the state of whatever matter is present. It says nothing about how much energy that matter can actually transfer to another object. A region can be technically hot and thermally empty simultaneously. Most of the apparently hot regions of the universe are exactly this thermally empty spaces, where the few particles present happen to be moving very fast, contributing nothing meaningful to the thermal environment of anything that passes through them. The architecture of cold is therefore even more complete than the void statistics alone suggest. It is not merely that 80 to 90% of the universe's volume lies in structures where temperatures are near the cosmic floor. Even the remaining 10 to 20%, the filaments and clusters and galaxy-bearing regions, is thermally dominated by cold vacuum between the rare objects that actually produce or retain meaningful heat. The warm fraction of the warm fraction is itself vanishingly small. Cold is not a feature of the universe. Cold is the universe. It is the material out of which all other features are carved, the default condition, the resting state, the answer the cosmos gives to every thermal question, when no star or black hole or collapsing gas cloud is nearby to complicate the answer. The stars and galaxies are not embedded in a universe that happens to be cold. They are embedded in cold the way islands are embedded in ocean. The ocean does not exist because of the islands. The islands exist despite the ocean. And the ocean is very, very large. What those islands of warmth are, how hot they burn, how brief their lives, how vanishingly small their volume compared to the cold that surrounds them, is the next chapter of this story. 1118, Claude responded. There is a star burning right now approximately 640 light-years from Earth. There is a star burning right now approximately 640 light-years from Earth. Its name is Betelgeuse, and it sits in the shoulder of the constellation Orion, visible on clear winter nights as a distinctly reddish point of light near the upper left of the familiar hourglass pattern. Betelgeuse is not a typical star. It is a red supergiant, a category of stellar object, so extreme in its dimensions that the word large fails to carry any useful meaning when applied to it. If Betelgeuse were placed at the center of our solar system in the position currently occupied by the Sun, its outer atmosphere would extend past the orbit of Jupiter. It would swallow Mercury, Venus, Earth, Mars, the entire asteroid belt, and Jupiter itself with room remaining. Every planet on which humans have ever trained a telescope, every world we have ever visited with a spacecraft, every destination in the inner solar system that has ever been discussed as a candidate for human exploration, all of it would exist inside this single star. Betelgeuse burns at a surface temperature of approximately 3500 Kelvin. Its luminosity, the total power output in all directions, is roughly 1,000,000 times greater than the Sun. The energy it releases every second would power human civilization at its current consumption rate for an interval so long it has no name in common language. It is by any measure that humans instinctively apply to size one of the most enormous objects in the observable universe. And it is a firefly in a cathedral. This is the central fact about stellar heat in the universe. Not that stars are not genuinely hot, they are extraordinarily so. Not that their energy output is not genuinely vast, it is beyond any comfortable comparison to human-scale quantities. The central fact is proportion. The ratio of the volume occupied by stars to the volume of the space that contains them is a number so small that it requires scientific notation with a negative exponent large enough to make the expression feel more like philosophy than arithmetic. Begin with the Sun, because the Sun is the star we know best, and the one whose dimensions we can discuss with some confidence in the listener's ability to follow. The Sun's radius is approximately 696,000 kilometers. Its volume is roughly 1.41 times 10 to the power of 18 cubic kilometers. That is a large number. By any human standard, it is an incomprehensible number. You could fit approximately 1.3 million Earths inside the Sun. If you hollowed out the Sun and filled it with golf balls, you would need a quantity of golf balls that exceeds the number of seconds that have passed since the Big Bang by many orders of magnitude. Now, consider the space the Sun occupies within the Milky Way. The Milky Way's disk has a volume of roughly 8 to 10 trillion cubic light-years. 1 light-year is approximately 9.46 times 10 to the power of 12 kilometers. A cubic light-year is therefore approximately 8.47 times 10 to the power of 38 cubic kilometers. The Sun's volume expressed in cubic light-years is approximately 1.67 times 10 to the power of negative 21 cubic light-years. A decimal point followed by 20 zeros, followed by the digits 167. Divide the Sun's volume by the volume of the Milky Way. The result is a fraction on the order of 10 to the power of negative 34. The Sun occupies roughly 1/10,000th of a billionth of a billionth of a billionth of the Milky Way's volume. If you represented the Milky Way as the entire surface area of the Earth, the Sun would occupy a patch smaller than a single bacterium. And the Sun is not small as stars go. It is a middle-sized, middle-aged, thoroughly average yellow dwarf. The galaxy contains stars ranging from tiny red dwarfs with radii a fraction of the Sun's to bloated supergiants like Betelgeuse hundreds of times larger. Averaging across the stellar population and accounting for the fact that red dwarfs are far more numerous than any other type, the average star is considerably smaller than the Sun. The fraction of galactic volume occupied by stellar interiors, when calculated honestly across the entire stellar population, does not improve meaningfully from the estimate derived from the Sun alone. Stars are small, the galaxy is large, the ratio between them is crushing. Now extend this to the observable universe. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains on average somewhere between 100 billion and several hundred billion stars, though the range is enormous. Dwarf galaxies may contain only a few billion stars, while giant elliptical galaxies can contain trillions. Taking a conservative average of roughly 100 billion stars per galaxy and 2 trillion galaxies yields an estimate of approximately 10 to the power of 23 stars in the observable universe. That is roughly 100 sextillion stars. 100 sextillion furnaces, each burning at thousands of degrees on its surface and millions of degrees in its core, each fusing hydrogen or helium or heavier elements into energy, each radiating power outward in all directions into the surrounding void. The total volume of the observable universe is approximately 4.1 times 10 to the power of 80 cubic meters. The total volume of all stellar interiors, taking an average stellar volume somewhat smaller than the Sun's and multiplying by 10 to the 23rd stars, yields roughly 10 to the power of 51 cubic meters of hot stellar material in the entire observable universe. Divide stellar volume by total cosmic volume. The result is approximately 10 to the power of negative 29. Stars occupy roughly 1 billionth of 1 billionth of 1 billionth of the observable universe's total volume. Everything else is void. Cold, dark, radiation-filled void, sitting at temperatures near 2.725 Kelvin, with no stellar furnace nearby to deviate the local temperature by any significant amount. 1 billionth of 1 billionth of 1 billionth. Sit with that for a moment. Not as an abstraction, not as a number to be processed and filed away, but as a physical fact about the place you inhabit. The universe you live in is a structure in which the hot, luminous, life-sustaining fraction occupies less than 1 part in 10 to the 29th of the available volume. The fraction of the cosmos that is warm in the sense of containing stellar interiors or surfaces is so small that if you selected a random point anywhere in the observable universe, the probability of landing inside a star would be comparable to the probability of throwing a grain of sand from a moving car on a highway and hitting a specific atom in a specific blade of grass somewhere in a field the size of a continent. Yet despite these proportions, stars produce everything that makes the universe interesting. They are the only natural sites of nuclear fusion in the modern cosmos, the only factories where elements heavier than lithium are forged, the only power sources capable of warming planetary surfaces to temperatures compatible with liquid, water, and complex chemistry. Without stars, the universe would be nothing but cold hydrogen, cold helium, and cold darkness from one edge of the observable horizon to the other. Stars are cosmically negligible in volume and absolutely essential in function. They are the rarest important things in existence. The stars themselves span an enormous range of thermal conditions. At the cool end of the stellar spectrum sit the red dwarfs, the most numerous type of star in the observable universe. Approximately 70% of all stars in the Milky Way are red dwarfs. They have surface temperatures ranging from roughly 2500 to 4000 Kelvin. They are dim, they are small, and they are extraordinarily patient. A red dwarf of the lowest mass burns its hydrogen so slowly that its expected lifespan exceeds the current age of the universe by factors of 100 or more. The most miserly red dwarfs will still be burning 10 trillion years from now, long after every star more massive than they are has exhausted its fuel and gone dark. Not a single red dwarf in the observable universe has yet run out of hydrogen. Every red dwarf that has ever ignited is still burning. Not one has died. They are the longest-lived sources of warmth in the universe, these dim, cool, patient stars. Their surfaces glow a deep orange-red, too faint to see with the naked eye from even modest distances. From Earth, not one of the billions of red dwarfs in the Milky Way is visible without a telescope, despite the fact that they constitute the overwhelming majority of the stellar population. They are the dominant type of star in the cosmos, and completely invisible to unassisted human vision. At the hot end of the stellar temperature range sit the blue supergiants and blue hypergiants. Stars like Eta Carinae, a hypergiant, approximately 7500 light-years from Earth in the Carina Nebula, have surface temperatures exceeding 36000 Kelvin and luminosities approaching 5 million times that of the Sun. They burn with such ferocity that their lifespans are measured in millions of years rather than billions. They are prodigal in the most literal sense, spending their thermal inheritance so rapidly that they exhaust in a brief cosmic instant what a red dwarf would nurse across trillions of years. Eta Carinae experienced a massive outburst in the 1840s that made it briefly the second brightest star in the night sky, outshone only by Sirius. Astronomers watching it from Earth using the telescopes available at the time recorded its sudden brightening with amazement. The event they observed had actually occurred 7500 years earlier, the light from the outburst taking that long to cross the distance between Eta Carinae and Earth. By the time human eyes registered the brightness, the event itself was ancient history. Eta Carinae is currently expected to end its life in a supernova or hypernova explosion that may, when it occurs, be visible in daylight from Earth. Between these extremes, red dwarfs and blue hypergiants, lies the full range of stellar thermal conditions. Every star you can see in the night sky represents a different point on this spectrum, a different balance between mass and fuel consumption, and surface temperature and luminosity. The night sky is a thermal museum, a collection of burning spheres at different stages of their lives. Different positions on the path from hydrogen-burning main sequence stars to whatever final state their mass dictates. But stars are not the hottest things in the modern universe. That distinction belongs to the environment surrounding stellar mass black holes and supermassive black holes, specifically the accretion disks that form when matter spirals inward toward the event horizon. When gas and dust fall toward a black hole, they do not drop straight in. Conservation of angular momentum, the same physical principle that causes a figure skater to spin faster when pulling in their arms, causes the infalling material to spiral. As it spirals inward, it forms a flattened disk of material orbiting the black hole at increasing speeds. Friction between adjacent layers of this disk, moving at different orbital velocities, converts kinetic energy into heat. The inner regions of the disk, where orbital speeds approach a significant fraction of the speed of light, reach temperatures that dwarf anything achievable in stellar interiors. Around stellar mass black holes formed from the collapse of massive stars, typically containing between a few and a few dozen solar masses, inner accretion disk temperatures reach into the tens of millions of Kelvin. Around supermassive black holes of the kind that sit at the centers of large galaxies, the temperatures climb higher still. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, and containing approximately 4 million solar masses, produces modest thermal output by the standards of its class, because it is currently accreting very little material. But the most actively feeding supermassive black holes, those at the centers of galaxies, with abundant infalling gas, power phenomena, called quasars, objects so luminous that they outshine the combined light of every star in their host galaxy by factors of hundreds or thousands. Quasar accretion disks achieve temperatures approaching hundreds of millions of Kelvin in their innermost regions. Some measurements suggest that the most energetic regions of the most extreme quasar environments reach temperatures of 1 billion Kelvin or more. These are among the highest sustained temperatures in the modern universe, exceeded in peak value only by the fleeting conditions inside supernova explosions. A supernova represents a thermal event of a completely different character, not sustained, not ongoing, but instantaneous in the sense that matters cosmically. When a massive star exhausts the nuclear fuel in its core, the core collapses in a fraction of a second. The mass of the Sun compressed into a sphere, roughly the size of a city, implodes at velocities approaching a quarter of the speed of light. The collapse is halted by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state when the core density reaches approximately 10 to the power of 17 kilograms per cubic meter. That is 100 million billion kilograms per cubic meter, a density at which a single teaspoon of core material would weigh roughly 1 billion tons. The implosion rebounds from this extraordinarily dense core, sending a shockwave outward through the star's outer layers. In the first seconds of core collapse, the temperature at the center reaches approximately 100 billion Kelvin, 100 billion degrees. That is hotter than the interior of any stable star, hotter than any accretion disk around any black hole. It is a temperature the universe has not routinely produced since it was less than 1 second old. A dying star briefly recreates the thermal conditions of the primordial cosmos. In those first seconds, the collapsing core produces neutrinos, nearly massless particles that interact so weakly with matter that they can pass through the entire diameter of the Earth with only a tiny probability of interacting with a single atom. The supernova releases more energy in its first 10 seconds through neutrino emission than the Sun will release in its entire 10 billion year lifetime. The energy is real, the temperature is real. The thermal event is among the most violent in the history of the cosmos. And then it ends. The explosion expands outward, the temperature drops, the shockwave sweeps up surrounding interstellar gas, creating an expanding shell of hot material called a supernova remnant. For thousands of years after the initial explosion, the remnant glows X-rays, visible light radio waves, as the shocked gas gradually cools and disperses into the interstellar medium. Eventually, the remnant merges with the surrounding gas. Its thermal energy spread across light years of space until it becomes indistinguishable from the background. The Crab Nebula, the remnant of a supernova, observed by Chinese astronomers in 1054 CE, spans approximately 11 light-years today. At its center sits a pulsar, a rapidly rotating neutron star, spinning approximately 30 times per second and powering the nebula's continued X-ray and visible light emission. The supernova that created it was briefly visible in daylight for approximately 23 days. Today, nearly 1,000 years later, the remnant is still hot enough to glow in X-rays, still energized by the neutron star at its core, but it is cooling, spreading, diluting. The thermal violence of its birth is being slowly swallowed by the cold of the surrounding interstellar medium. This is the pattern that applies to every source of high-temperature thermal energy in the universe. Stars, accretion disks, supernova remnants, all of them burn or glow or radiate for finite periods, then cool and fade. The energy they release does not disappear. Energy is conserved, distributed across ever-growing volumes of expanding space, but it dilutes, it thins, it redshifts toward longer wavelengths and lower frequencies. It joins the general background radiation of the cosmos, contributing an infinitesimal increment to the thermal noise of the universe, before becoming indistinguishable from the ancient microwave glow. Every stellar fire is a temporary event in impermanent cold. The analogy that captures this most accurately is not a campfire in a dark forest, which implies a contained, bounded darkness that the fire genuinely illuminates and warms. It is something more extreme. Imagine the Pacific Ocean on a clear night. Every star in the universe is a spark. Not a fire, not a flame, a spark. Tiny, hot, brief. The sparks are real. Each one burns with genuine heat. Some burn hotter than others, some last longer. But the Pacific Ocean is very, very large. And the temperature of the Pacific Ocean is not determined by the sparks that occasionally ignite above its surface. The ocean's temperature is determined by its own thermal properties, its depth, its currents, its relationship with the atmosphere above it. The universe is the ocean. The cosmic microwave background is its thermal character. The stars are the sparks. And the Pacific Ocean is not warm because sparks occasionally appear above it. There is one more source of thermal energy in the universe that deserves mention here, not because it is hot in the conventional sense, but because it reveals something profound about the future thermal history of the cosmos. It is the radiation that black holes produce, not through accretion, but through a quantum mechanical effect discovered theoretically by Stephen Hawking in 1974. Hawking radiation arises from the behavior of quantum fields near a black hole's event horizon. In the vacuum of space, pairs of virtual particles continuously appear and annihilate in timescales too short to violate the uncertainty principle. Near an event horizon, occasionally one member of such a pair falls inside the horizon before annihilation can occur. The other escapes as real radiation. From a distant observer's perspective, the black hole appears to emit a faint thermal radiation with a temperature inversely proportional to the black hole's mass. For stellar mass black holes, the Hawking temperature is on the order of 10 to the power of -8 Kelvin. That is 100 millionth of a Kelvin, colder than the cosmic microwave background by a factor of about 27 million. The radiation is utterly undetectable with any current or foreseeable instrument. In the current universe, black holes absorb far more energy from the cosmic microwave background than they emit through Hawking radiation, so they are effectively growing rather than shrinking. But in the far future, when the universe has expanded and cooled to temperatures below even the Hawking temperature of small black holes, the balance will reverse. Black holes will begin losing mass to Hawking radiation faster than they gain it from the background. They will slowly, impossibly, slowly evaporate. And in their final moments of evaporation, they will produce a brief burst of thermal radiation, a tiny flash of heat in the cold, dark universe, the last thermal event before a silence that has no end. The stars are the warmth of the present, the black holes are the warmth of the deep future, and both are negligible fractions of a universe whose defining thermal character is the cold, dark quiet of 2.725 Kelvin, spreading in every direction from every point in space, older than any star, more uniform than any other feature of the cosmos, and more patient than anything that burns. 1121, Claude responded. The universe has a biography. The universe has a biography. Like all biographies, it has a beginning, a middle, and an end. Unlike most biographies, the ending is not a moment but a condition, a state. The cosmos will approach asymptotically across timescales so vast that the numbers used to express them bear no intuitive relationship to any duration humans have ever experienced or imagined. The story of the universe's future is the story of heat, leaving and never returning. It is the story of light fading and never being replaced. It is the story of the cold winning not through any active conquest, but through the simple arithmetic of entropy, the universe's irreversible tendency to move from concentrated energy toward diffuse equilibrium, from order toward a disorder, from warmth toward the cold that was always waiting. Physicists who study the long-term evolution of the cosmos have divided its future history into eras. Not arbitrary divisions, but phases defined by the dominant physical processes operating during each period. What types of objects exist? What sources of energy remain available? What thermal conditions prevail across the majority of cosmic volume? These eras follow one another in sequence, each one colder and darker and longer than the one before, each one making the previous era look, by comparison, like a brief and brilliant flicker. We currently live in what cosmologists call the stelliferous era. The word comes from the Latin for star-bearing. It is the era of stars, the period during which nuclear fusion occurs in stellar cores across the observable universe, producing light and heat and the heavier elements from which planets and living things are made. The stelliferous era began approximately 100 to 200 million years after the Big Bang, when the first generation of stars ignited from primordial clouds of hydrogen and helium. It will end when the last star exhausts its fuel and goes dark. The first stars were different from those we observe today. Formed entirely from hydrogen and helium, the only elements the Big Bang produced in significant quantities, they contained none of the heavier elements that later stellar generations would create and disperse through supernova explosions. Astronomers call these first stars population 3 stars, and while none has ever been directly observed, they formed and died billions of years before any of the light reaching us today originated from their era. Their existence is inferred from theoretical models and from the composition of the oldest observable stars, which contain only tiny traces of elements heavier than helium. Population 3 stars were likely massive enough that their lives were extraordinarily brief by stellar standards, perhaps only a few million years. They burned hot, fused, heavy elements in their cores for the first time in cosmic history and ended their lives in violent supernova explosions that seeded the surrounding gas with carbon, oxygen, nitrogen, iron, and the other elements that subsequent stellar generations would incorporate. Every atom in your body heavier than hydrogen was produced inside a star, not the Sun, which has not yet reached the stage of its life, where it fuses elements beyond helium, but in stars that lived and died before the Sun was born. You are made of stellar ash. The iron in your blood was forged in the core of a massive star that exploded billions of years ago and scattered its material into the interstellar medium from which the solar system eventually condensed. The star formation rate, the mass of new stars igniting per year across the Milky Way, peaked approximately 10 billion years ago, roughly 3 to 4 billion years after the Big Bang. At that peak, the universe was forming stars at a rate perhaps 10 to 30 times higher than it does today. The cosmic star formation rate has been declining ever since, as the raw material for stellar birth, cold clouds of hydrogen gas, is gradually consumed by successive generations of star formation. Stars form from gas. When they die, some of that gas returns to the interstellar medium through stellar winds and supernova ejecta, but not all of it. Some is locked away permanently in stellar remnants, white dwarfs, neutron stars, black holes that will never return their mass to the star-forming gas reservoir. With each generation, the available fuel diminishes slightly. The Milky Way currently forms new stars at a rate of roughly 2 to 3 solar masses per year. That sounds substantial, until you remember that the galaxy contains 200 to 400 billion stars each, representing 1 to many solar masses of material locked up in a stellar life cycle. The star formation rate is low. The raw material is dwindling. The galaxy is not in decline in any dramatic sense. It will continue forming stars for billions of years to come, but the trajectory is clear. The era of stellar birth is past its peak. We live on the descending slope. Sun-like stars, stars within a factor of 2 or 3 of the Sun's mass, will continue forming and burning for tens of billions of years. The universe at its current age of 13.8 billion years is young enough that stars like the Sun have many generations yet to live and die. But the clock is running. The hydrogen that fuels stellar fusion is a finite resource. It is not replenished by any process in the universe. It was produced at the Big Bang and has been consumed in stellar cores ever since, converted to helium and heavier elements with each generation. The most massive stars, those 10 or more times the Sun's mass, have lifespans of only a few million years. They have been forming and exploding throughout the history of the galaxy, and will continue to do so as long as the gas supply permits. Each one lives fast, burns outrageously hot, and contributes its mass of heavy elements to the next generation of star-forming clouds. These stars are the most thermally violent objects in the stelliferous era, but their individual contributions to cosmic warmth are brief compared to the era itself. The Sun has approximately 5 billion years of stable hydrogen burning remaining in its main sequence lifetime. After that, its core will exhaust its hydrogen supply. Without the outward pressure of nuclear fusion to support it against gravitational collapse, the core will contract and heat. The increased temperature will ignite hydrogen fusion in a shell surrounding the inert helium core. The extra energy from this shell burning will cause the Sun's outer layers to expand dramatically. The Sun will become a red giant swelling to perhaps 200 times its current radius. The surface will cool as it expands, dropping from its current 5500 Kelvin to perhaps 3500 Kelvin. But the enormous surface area of the expanded star will pour far more total radiation onto the inner solar system than the current Sun does. Long before the Sun reaches its red giant phase, its gradually increasing luminosity will have rendered Earth uninhabitable. Stars like the Sun grow slowly brighter over their main sequence lifetimes as the changing composition of the core alters its structure. In approximately 1 billion years, the Sun's luminosity will have increased by roughly 10%. That increase is sufficient, models suggest, to trigger a runaway greenhouse effect on Earth, a process in which increased solar heating causes more water to evaporate, which increases the greenhouse warming, which causes more evaporation until the oceans are entirely vaporized and the surface temperature climbs to hundreds of degrees. The process once started cannot be reversed by any natural mechanism on Earth. The oceans will not return. The habitable planet we know will be gone, not dramatically destroyed, but slowly, irreversibly baked. This is Earth's individual future in the thermal evolution of the solar system. The sun's gift of warmth carries an expiration date written in stellar physics. The warmth that created life will eventually destroy it, not out of malice or indifference to any particular outcome, but simply because the physics of stellar evolution dictates that sun-like stars increase in luminosity as they age, and the narrow temperature window compatible with liquid water is sensitive enough to be disrupted by changes of just a few percent in stellar output. But Earth's fate, while sobering, is local. The broader future of the cosmos extends across timescales that make Earth's 5 billion remaining years look like the opening scene of a film that lasts 1,000 years. After the sun's red giant phase, it will shed its outer layers into space as a planetary nebula, a glowing shell of expelled gas illuminated by the hot remnant core left behind. That core, roughly the mass of the sun compressed into a sphere roughly the size of Earth, will be a white dwarf. Composed primarily of carbon and oxygen, it will have no internal energy source. No fusion will occur. It will simply radiate away the thermal energy accumulated during the sun's life, cooling slowly over billions of years. White dwarfs begin their existence very hot. Some are initially hotter than the surfaces of the most massive blue supergiants, reaching temperatures of 1,000,000 Kelvin or more in the first moments after the planetary nebula disperses, but they cool. Steadily, inevitably, they move through the temperature scale from blindingly hot to white hot to yellow hot to orange to red to infrared to microwave shedding energy into the surrounding void with nothing coming in to replace it. A white dwarf produces no new energy. It is an ember, not a fire. The cooling timescale for a white dwarf is extraordinarily long. Current models suggest that a white dwarf requires approximately 10 to 15 billion years to cool from its initial temperature to a surface temperature of around 4,000 Kelvin. The universe at its current age is not old enough for any white dwarf to have cooled below about 4,000 Kelvin. Every white dwarf that has ever formed is still hot enough to emit detectable radiation. None has yet reached the final cold state that physics predicts for them, a state so cold it has been given its own name, a black dwarf. A black dwarf is a white dwarf that has cooled to thermal equilibrium with the cosmic background radiation. At that point, it emits essentially no radiation, reflects no light, and is detectable only through its gravitational influence. It is, in every practical sense, dark, invisible, a cold, dense remnant of a star smaller than the Earth, containing roughly the mass of the sun floating in the void, without emitting a single photon of significance. No black dwarfs currently exist in the universe. The cooling time required to produce one exceeds the current age of the universe by a factor of 100 or more. The youngest black dwarfs, the first ones to reach complete thermal equilibrium with the surrounding cosmos, will not form for trillions of years. This is the future that awaits most stars. Not a dramatic explosion, not a collapse into a black hole, simply cooling. The same process that the cosmic microwave background itself has undergone, the same dilution and dispersal that has brought the primordial fire down to 2.725 Kelvin, operating on the remnants of stellar evolution rather than on the aftermath of the Big Bang. Everything that generates heat eventually stops generating heat. Everything that holds heat eventually loses it. The direction of time is the direction of cooling. The era that follows the stelliferous era is called the degenerate era. It is defined not by the absence of matter. Matter remains, but by the absence of active nuclear fusion. The dominant objects in the degenerate era are the cooling remnants of dead stars, white dwarfs slowly becoming black dwarfs, neutron stars cooling from their initial billions of degrees toward the cosmic floor, and the occasional isolated, a planet or brown dwarf drifting through the dark. No stars burn, no stellar nurseries glow, no supernova explosions light up the darkness for weeks. The universe is dark in a way it has not been since before the first stars ignited. The degenerate era will last from roughly 1 trillion years after the Big Bang, which is roughly 70 times the current age of the universe, to perhaps 10 to the power of 40 years. These numbers are not meaningful in any conventional sense. The human brain, shaped by evolution for survival on a timescale of decades, is not equipped to process durations of this magnitude. 10 to the 40 years is to the current age of the universe, as the current age of the universe is to 1/300,000th of a second. It is not merely a long time. It is a duration for which human language has no adequate tools. During the degenerate Gatsa, the dominant thermal story is slow cooling, white dwarfs becoming black dwarfs, neutron stars losing their residual heat, the universe growing darker and colder with each passing trillion years. The average temperature of any object left alone in the void slowly converging on the cosmic background temperature, which is itself still declining as the universe continues to expand. One source of heat persists in the degenerate era that is not immediately obvious: proton decay. If it occurs, and current theories beyond the standard model suggest it might, though it has not yet been observed experimentally, would provide a small but persistent energy source inside the degenerate matter of cooling white dwarfs and black dwarfs. Each proton that decays releases a tiny burst of energy that briefly heats the surrounding material. The expected proton decay timescale is roughly 10 to the power of 34 years. This is far longer than any current observation can probe. No experiment has yet detected a single proton decaying, but if it occurs, it would mean that black dwarfs are not completely cold. They would maintain a faint residual warmth, a surface temperature of perhaps a few hundred Kelvin sustained by the slow release of energy from decaying protons throughout their interiors. If protons decay, black dwarfs glow faintly for a very long time. Eventually, the last proton decays, the last energy is released, and the glow ends. The object cools to the background temperature and stays there. If protons do not decay, black dwarfs simply cool until they reach thermal equilibrium with the background and then sit cold and dark, essentially forever. Either way, the endpoint is the same. After the degenerate era comes the black hole era. It begins when the last white dwarfs and neutron stars have either decayed through proton decay or been captured by black holes through gravitational interactions in the remnant galaxy clusters that persist through the degenerate period. The dominant objects in the universe are now black holes, supermassive black holes that once sat at the centers of galaxies, stellar mass black holes left behind by supernova explosions throughout the stelliferous era. The universe contains essentially nothing else of significance. No stars, no planets, no gas clouds, no radiation sources except the fading cosmic background and the Hawking radiation emitted by the black holes themselves. Hawking radiation provides the last source of thermal energy in the universe. It is unimaginably faint. A stellar mass black hole emits Hawking radiation at a temperature of roughly 10 to the -8 Kelvin. A supermassive black hole emits at a temperature billions of times lower still. These temperatures are far below the current cosmic background temperature. In the black hole era, however, the background temperature itself has dropped. The universe has expanded enormously since the present, and the background radiation has cooled proportionally. By the time the black hole era begins, the background temperature may have dropped to values far below even the Hawking temperature of stellar mass black holes. At that point, the black holes begin losing mass to Hawking radiation faster than they gain it from the background. They begin slowly and imperceptibly, slowly to evaporate. A stellar mass black hole takes approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. A black hole containing the mass of 1 billion suns requires approximately 10 to the power of 99 years. The largest supermassive black holes, those with masses of tens of billions of solar masses, may require 10 to the power of 100 years or more, a duration called a googol, to evaporate. These timescales are incomprehensible. The stelliferous era, all 100 trillion years of it, is shorter relative to the evaporation time of a supermassive black hole than 1 second is to the current age of the universe. The era of stars, the entire period during which any star in the universe has ever burned, from the first population 3 stars to the last cooling red dwarf, occupies less than 1/1,000,000th of the time required for a supermassive black hole to evaporate. When the final black hole completes its evaporation, it does so in a brief burst of radiation. The last moments of a black hole's evaporation are rapid. As the mass decreases, the Hawking temperature increases, accelerating the energy loss. The final instant of a black hole's existence releases a pulse of high-energy radiation, a brief flash of warmth in the cold, dark universe. And then nothing, no object remains. Only the diffuse radiation from the evaporation spreading outward, redshifting, cooling, joining the general background. After that comes the era that has no name because it has no events. No objects remain to define events. Only an expanding, cooling, nearly perfectly uniform sea of extremely low-energy photons and other fundamental particles drifting apart in a void that grows larger with every passing moment and colder with every increment of expansion. The background temperature falls below 10 to the -30 Kelvin, then below 10 to the -60, then lower still, approaching but never quite reaching absolute zero as the universe expands toward a size that has no upper bound. This is the heat death of the universe, not a dramatic ending, not a collapse or an explosion or a final catastrophic event, a state. An equilibrium so complete and so cold that no thermodynamic process can extract energy from any temperature difference because no temperature differences exist. Everything is the same temperature. Everything is as cold as everything else. The maximum entropy state, the condition from which no structure, no complexity, no information processing of any kind can emerge. If you represented the entire future history of the universe as a symphony, every era, every process, every source of heat, from the first stars to the last evaporating black hole, the stelliferous era would be the opening note. Not the opening movement, not the first theme, the opening note. A single sound at the very beginning of the first measure. Everything that follows the degenerate era, the black hole era, the long approach to heat death, is the music. Vast, dark, silent music played over durations that make the opening note invisible on any reasonable score. We live inside that opening note. Every star that has ever burned, every supernova that has ever blazed, every planet that has ever been warmed by orbiting a stellar furnace, every ocean that has ever remained liquid, every living thing that has ever existed anywhere in the observable universe. All of it fits inside the opening note. The rest of the symphony is silence growing colder, with each passing measure approaching a final, sustained note of absolute stillness that the orchestra will hold forever. The cold does not win in the end. The cold was always winning. The warmth was always the exception. The symphony was always going to end this way. The only question was how long the opening note would last, and how much it would mean to the things that existed within it. Come back to the room you are sitting in. Not metaphorically, literally. The specific room, the specific chair or floor or bed, the specific temperature of the air against your skin right now. Feel it, not as an abstraction, not as a data point in a larger argument, but as a physical fact about your immediate environment. The air touching you is warm, not warm relative to the surface of the sun, not warm relative to the core of the earth, but warm in the only sense that has ever mattered to any living thing on this planet, warm enough. Warm enough for the water in your cells to remain liquid. Warm enough for the proteins in your body to maintain their shapes. Warm enough for the electrochemical reactions in your neurons to proceed at the speeds required for thought, for memory, for the processing of everything you have just heard. You are sitting in one of the warmest places in the observable universe. Not one of the hottest. The surface of the sun is hotter. The core of a collapsing star is hotter by a factor of billions. The inner regions of an accretion disk around a supermassive black hole are hotter still. But hot and warm are not the same thing. Hot is a temperature. Warm is a condition. Warm means within the range where complexity is possible, where chemistry builds rather than destroys, where water flows rather than freezes or boils, where the molecular machinery of life can operate without being torn apart by thermal violence or frozen into immobility. The range of temperature compatible with that complexity is narrow, extraordinarily narrow, from approximately 0 degrees Celsius at the cold end to perhaps 120 degrees at the upper limit, where the most heat-tolerant life forms known to science can survive. A range of roughly 120 degrees on a cosmic temperature scale that spans from 2.725 Kelvin to tens of billions of degrees in stellar interiors. The habitable temperature range occupies less than 1/10,000,000th of the thermal spectrum that exists in the universe, and Earth sits within it, has sat within it for approximately 4 billion years, long enough for single-celled life to evolve into multicellular life, for multicellular life to diversify into the astonishing variety of organisms that share this planet, for one particular branch of that diversity to develop nervous systems complex enough to ask questions about the temperature of the universe they inhabit. Hold what you now know and let it settle. The universe defaulted to 2.725 Kelvin within the first few 100,000 years of its existence, when the primordial fire had cooled enough for atoms to form and release the light that has been traveling ever since. That default temperature has been declining for 13.8 billion years, as expansion stretches the background radiation toward longer wavelengths and lower energies. The overwhelming majority of the universe's volume, somewhere between 80 and 90%, by the most conservative estimates, exists inside cosmic voids, where no galaxy forms in meaningful numbers, where no star burns, where the thermal environment is determined almost entirely by that ancient microwave glow. Even outside the voids within the filaments and clusters where galaxies concentrate the volume between stars, is cold, dark vacuum at temperatures near the cosmic floor. The hot objects, stars, accretion disks, supernova remnants are real, their heat is real, but their combined volume amounts to roughly 1/1000,000th of 1/1000,000th of 1/1000,000th of the observable universe's total volume. Everything that burns, everything that glows, everything that generates or sustains heat through any physical process known to science, occupies a share of cosmic space so small that expressing it as a fraction requires negative exponents that exhaust the patience of anyone trying to communicate them as intuitive quantities. The warm places where liquid water is possible, where chemistry builds, where life might exist, are rarer still. They are a fraction of the already negligible fraction. They depend not merely on the presence of a star, but on the precise orbital distance of a rocky planet, the mass and composition of that planet, the character of its atmosphere, the strength of its magnetic field, the stability of its axial tilt, the availability of liquid water in the right quantities, the geological activity required to cycle carbon and regulate temperature over geological time. Each additional requirement filters the candidates further. Each layer of specificity reduces the count. Earth meets all of these requirements simultaneously. It has met them continuously without interruption for approximately 4 billion years. Long enough for the processes of evolution to produce from simple chemistry the complexity we call life, and from life the further complexity we call consciousness, and from consciousness the capacity to look outward at the universe and ask what it is and how it works and what it means. That capacity, the capacity for the universe to know itself through the minds of creatures small enough to stand on the surface of a rocky planet, is itself extraordinary. Not in any mystical sense, not as evidence of intent or design or purpose embedded in the fabric of the cosmos, but extraordinary as a fact. The universe is 13.8 billion years old. It contains 2 trillion galaxies. It is 99.9999999% cold, dark void, and in one corner of one galaxy, on one planet orbiting one unremarkable star matter, has arranged itself into structures complex enough to reconstruct the thermal history of the entire cosmos, from first principles using instruments built from elements forged in stellar cores powered by energy from a star processed by brains that themselves represent 4 billion years of accumulated evolutionary complexity. The universe produced something capable of understanding the universe. In a cosmos defined by its coldness, by its emptiness, by its indifference to the existence of anything complex or ordered or aware that happened. It did not have to happen. Nothing in the laws of physics required it. The equations that govern the behavior of matter and energy are indifferent to whether any particular arrangement of atoms produces consciousness or merely drifts through the cold dark as an inert collection of particles. The universe does not require witnesses. It does not require minds. It proceeded for 9 billion years without them, expanding and cooling and forming stars and planets and complex chemistry in total silence, with no one to observe any of it or ask what it meant. The witnesses arrived late and occupy an almost inconceivably small fraction of the available space and time. But they arrived. You arrived. Right now in that room at that temperature within that narrow band of warmth that the cosmic cold surrounds on all sides and in all directions. You arrived in time to ask these questions, to build these instruments, to measure this background radiation, to reconstruct this history, to understand in the only way that matters, which is genuinely and with accurate information what kind of universe you live in and what your presence within it represents. What it represents is this: you are a temporary concentration of order in a universe that defaults to disorder. You are a local exception to a cosmic rule. You are warmth in a cold universe, complexity in a simple universe, awareness in an indifferent universe. Not because the universe made an exception for you, not because you are the purpose of the cosmos or its intended destination, but because the physics of stellar nucleosynthesis produced the carbon you are made of, and the gravitational dynamics of a young solar system placed a rocky planet at the right distance from the right star, and the geological and biological processes of 4 billion years on that planet, produced through mechanisms that required no guidance and served no goal. The particular arrangement of matter that is you, the warmth you feel, is not separate from this story. It is this story. The warmth of your body, 37 degrees Celsius, maintained by the metabolism of roughly 37 trillion cells, each one processing energy extracted from food, each one participating in the intricate chemical machinery that keeps the whole system running, is a direct continuation of the warmth of the Phaeum, the star that formed when a molecular cloud collapsed 4.6 billion years ago. The sun's energy arrives at Earth as photons. Plants capture those photons and store their energy in chemical bonds. You consume those bonds directly or indirectly, and your cells release the stored energy through oxidation, using it to maintain your temperature, to power your muscles, to sustain the electrochemical gradients across neural membranes that produce thought. You are the sun's energy concentrated and organized by 4 billion years of biological evolution into something capable of understanding its own origins. The cold surrounds this. The cold has always surrounded this. Even now, while you sit in this room at this temperature, the cold is present in the microwave background, photons passing through the walls, through your body, through the earth beneath you. The cold is 380 million light-years in every direction in the nearest cosmic void, sitting at 2.725 Kelvin, utterly unperturbed by the existence of anything warm or complex or alive. The cold will be present long after the sun expands and the oceans evaporate, and the last organism on Earth ceases to maintain its temperature against the growing heat of a brightening star. The cold will be present when the last star in the Milky Way exhausts its fuel and goes dark. It will be present when the last white dwarf cools to a black dwarf and the last black dwarf reaches thermal equilibrium with the background. It will be present when the last black hole evaporates in a faint burst of Hawking radiation and the universe settles into the perfect thermal uniformity of heat death. The cold will outlast everything. It will outlast every source of warmth that exists or will ever exist in the observable universe. It is the most patient thing in existence, and patience is the only quality required to win against warmth in the long run, because warmth is always temporary and cold is always the destination. But the cold has not won yet. Not here, not now. Here in this room, in this moment, the warmth is real and present and sustaining something extraordinary. It is sustaining the liquid water in your cells and the chemical reactions in your metabolism and the electrochemical processes in your brain that are right now constructing meaning from the sequence of sounds or words you are receiving. The warmth is enabling thought, enabling understanding, enabling the specific and remarkable experience of a mind comprehending its own cosmic context, knowing where it is, knowing how improbable its presence is, knowing what surrounds it and what will eventually replace it. That experience, the experience of understanding, is itself a form of warmth, not thermal warmth, something rarer. The warmth of a mind that knows it is alive, that knows it is temporary, that knows it is surrounded by a cold and indifferent universe, and that finds in that knowledge not despair but attention, not fear but clarity. The clarity of seeing things as they actually are, rather than as we might prefer them to be. The universe is not hospitable. It was not made for us. Its thermal default is a cold that makes our most extreme winters seem tropical. Its dominant structure is void, vast, dark, silent regions where nothing burns and nothing lives and nothing could. Its timeline makes our civilization, our species, our planet, our sun, look like a rounding error in an equation whose solution takes longer to write than the universe has existed. And yet the sun rises every morning over a planet that has liquid oceans. And yet cells divide, and organisms grow, and species evolve, and minds develop the capacity to measure the cosmic microwave background and reconstruct the thermal history of a universe that did not require them to exist, but somehow produced to them anyway. And yet you are here in this specific moment, warm, aware, capable of grasping the scale of the cold that surrounds you. That is not a small thing. It is in fact the largest thing there is, not in size but in significance. The universe can be described without reference to any living thing. The laws of physics operate identically whether or not any mind is present to observe or understand them. The cosmic microwave background would exist and would have the properties it has whether or not any instrument had ever been built to measure it. The expansion of the universe would proceed at the rate it proceeds regardless of whether any consciousness existed to notice. But the description would be incomplete in one specific and irreducible way. It would be a description without a describer, a story without a reader, a universe without the capacity to know itself. That capacity exists here, in this warm, improbable, temporary pocket of the cosmos. In the minds of creatures who emerge from stellar ash and planetary chemistry and 4 billion years of biological evolution, who built instruments from refined metals and engineered semiconductors, who pointed those instruments at the sky, and read in the patterns of ancient microwave radiation the complete thermal history of everything that has ever existed. We are the universe's memory of itself, fragile, temporary, absurdly improbable, but real, genuinely real. The warmth that made us possible is real. The cold that surrounds and will eventually reclaim everything is real. Both are true simultaneously, and holding both truths at once, the warmth and the cold, the significance and the brevity, the extraordinary improbability of presence and the absolute certainty of eventual absence, is the most honest relationship any mind can have with the cosmos it finds itself inhabiting. There is a heartbeat happening right now inside your chest. One heartbeat among perhaps 8 billion occurring simultaneously on this planet, on this warm, rocky world orbiting this particular star. Each heartbeat is a tiny mechanical event, muscle, contracting blood, moving pressure, fluctuating valves, opening and closing, with a precision that has been refined across hundreds of millions of years of cardiovascular evolution. Each one is powered by chemical energy derived from food, derived from sunlight, derived from a star 150 million kilometers away. Each one maintains the warmth of a body that is itself maintaining the conditions required for consciousness. In the cold dark of a cosmic void 380 million light-years from here, no heartbeat has ever occurred. In the frozen interstellar medium between the stars of the Milky Way, no heartbeat has ever occurred. In the long silence of the degenerate era, when the last stars have cooled to black dwarfs and the universe sits in trillion-year darkness, no heartbeat will occur. In the heat death that follows the perfect thermal equilibrium that the cosmos is slowly, inexorably approaching, no heartbeat will ever occur again. Your heartbeat is happening in the narrow window. The cosmically incomprehensibly narrow window between a cold past and a colder future, during which the universe contains enough concentrated warmth in enough local pockets to sustain the complexity required for life, for thought, for the specific experience of being alive and aware, and asking questions about the nature of the void that surrounds you. The universe chose cold. It chose cold at the moment of recombination when the primordial fire released its last photons and began its 13.8 billion year journey toward 2.725 Kelvin. It chooses cold with every passing second as the background radiation stretches further and cools further, and the total thermal energy of the cosmos dilutes across an ever-growing volume of expanding space. It will choose cold in the final silence of heat death, when the last quantum of usable energy has been spent and the last temperature difference has equalized, and nothing remains but the perfect, uniform quiet of maximum entropy. Against that choice, against that immense and patient and ultimately victorious cold, your heartbeat is happening right now. It is warm, it is brief, it is here. It is the most extraordinary thing in the observable universe, not because the universe was built to produce it, but precisely because it was not. Because the default answer to the question of what exists is cold, dark, empty void. Because the physics of this cosmos makes warmth the exception and cold the rule at every scale, from stellar neighborhoods to cosmic voids, to the long dark future of an expanding universe. Because against all of that, against the 2.725 Kelvin baseline and the trillion-year cooling of white dwarfs and the Google-year evaporation of black holes and the heat death at the end of everything warmth happened here. Step outside tonight. Look up. The stars you see are the exceptions. The darkness between them is the rule. Both are real. Both are yours to know. The universe is cold, nearly all of it, nearly all of the time. But not here, not yet. And in the time that remains, in the warmth that persists, in the heartbeats that continue, in the minds that keep looking outward and asking what it all means, there is something worth calling extraordinary. The cold will have the last word, but the warmth is speaking now.